Hello, everyone. Welcome back to the AAS YouTube channel, and this is part of the good stuff. This is the AAS Journal Author Series, and I'm very happy to have Trung and Yuan with us today. Hi there.
Hi.
Hi.
Let's see. It's a lovely day on this February 22nd, 2021, out in Phoenix. And so, what is your locations? Where are you at?
Texas.
Texas.
Yes.
Okay. Considering February 22nd, 2021, I could ask. How's your water? How's your power?
Everything's back to normal, at least for me. Yeah.
Yeah.
Texas is pretty big. What part of Texas are you in?
We're pretty close to Dallas.
No.
Yeah.
Yeah. I live right in Denton, and we didn't have power for around 3.5 or 4 days.
Okay.
Well, it was a rolling blackout, and then afterward we had boil water notice for another 1.5 days.
Yeah.
So that just ended about on Friday, I think. So I think everything's back to normal now.
Hopefully, I was hearing some news stories that people were getting $3,000, $17,000 electric bills for the month.
Right.
So,
Right. I don't know yet, but hopefully not.
Yeah, that will take some intervention, I'm sure. That's just out of bounds.
Yeah.
But cool. Well, I'm glad things are back to normal for you. Mostly normal. We'll see.
It makes us appreciate normal times more.
There you go. There you go. And Trung, you have this very lovely nebula. What is that?
Right. Thank you. It is the Orion Nebula. So this is M42 in the background. I think this is a Hubble telescope image, and it's taken in both visible and infrared combined.
Yeah. Cool. We might be talking about that. Or something.
Right. Maybe.
Yuan, you have this really lovely drawing over your left shoulder. Is that from one of yours?
From my son, yeah.
Very cool. Very cool.
It's actually his birthday today.
What a day. Happy birthday. What's his name?
Oscar.
Oscar, happy birthday.
Thank you.
How old is Oscar? 5?
5. Yeah.
What a guess. 5. Just because I reckon
that looks like
style of drawing is around 5-ish. So
yeah.
Very cool. Awesome. So Yuan and Trung, what do you like to do for research?
Well, I am a first-year graduate student, so I'm still figuring that out. I like astrophysics and in both theoretical and computational. And as of right now, I guess with this paper, I'm working on turbulence.
Yeah, that's a theoretical topic for sure over the decades, if not centuries. Yuan, what do you like to do for research?
So I'm mostly a theoretical / computational astrophysicist. Okay. Although this paper we're talking about today is mostly observational. Mm-hmm. And I do sometimes work on observational stuff. I'd say most of my research is actually about black holes. So I've looked at black hole accretion and black hole feedback. So I've looked at turbulence driven by black holes. This paper is actually the first time I ever thought much about stars. I know. I never thought that I would. Yeah, I never thought I would work on stars ever. I guess never say never.
Yeah, never say never. And this one is definitely got an observational bent to it. Mm-hmm. Very cool. New topics. Very good. Always good to learn new stuff.
Yeah.
And speaking of, let's go ahead and get into this really lovely APJ letter measuring turbulence with young stars in the Orion complex. And Trung and Yuan, take us away.
Oh, can I maybe tell a story of how it got started?
Absolutely.
Very briefly, although it's kind of a long story.
It's all great.
So because I like turbulence, I sort of always had this question in the back of my mind. We know that stars form out of turbulent clouds. So I always sort of wondered when the stars, at least the young stars, carry some of that memory, when the motions of stars have a little bit of that signature of turbulence of their parent clouds. I never acted on it. And then one day when I was still a postdoc fellow last year, when I was still a postdoc fellow at Berkeley, Marina Kunkel, one of the co-authors on this paper, came and gave a virtual colloquium. And she showed these beautiful data that she had analyzed. And so I thought, ooh, I could do something with that data. And so I talked to her and she's like, sure, I don't think anybody has done it. Go ahead, do it. And of course I didn't do anything about it because I'm mostly a theorist. And I never worked on stars. So I was like, yeah, sure, maybe one day I'll actually work on it. And then I was moving and stuff, so I was busy. I didn't really think much about it. And then I started at UNT last fall, and Trung said, I want to do a project with you. And I said, okay, here's like a list of 10 options, pick one. And then he picked this one. And I said, okay, this is actually pretty risky because nobody has done it. And it's not really what I used to work on, but I thought it was a cool idea. And then I said, but before we start, let me just make sure it's not a crazy idea. So then I talked to my friend Xiao Xu, who's a real expert on turbulence theory and interstellar medium. Yeah, that's also one of the co-authors. And I said, okay, tell me this idea is not crazy. And she said, no, I had the same idea. In fact, she said, yeah, when an observer came and gave a colloquium talk here, I thought, ooh, I could do something. And that was probably 2 years ago. Yeah, she said, oh yeah, and I even got the data. And I said, yeah, sure, my observer has better data. Yeah. And she said, okay, well, let's see. She said, let me forward an email to you.
Oh, we have verification.
So she forwarded me, yes, and that email is from Marina. So we were talking to the same observer because obviously she has the best data. That's perfect for this project. So we just came together and worked on it, and Trung worked so quickly that we were able to get something out within just a few months. So I'll let Trung talk about the science because he actually did most of the work.
I'll just interject one thing. We do have a video of Mariana talking about some of her.
I know, yeah. So it's very much related to that. Yep.
To her AAS Journal article video in the description below this video. Okay, Trung, take us away.
Okay, so with the data that Marina has from her paper back in 2018 about the stars in Orion. So from the data from Gaia and Apogee, we got, for the first time, we have 6-dimensional data, measurements of stars in the Orion complex. So that's 3-dimensional of space and 3-dimensional of velocities of all the stars. And using these data, so we compute, the data was broken down into 5 different groups within the Orion complex. So Orion A to D, and also the Lambda Ori cluster. And so with those 5 groups, we analyzed the data and we computed the first order velocity structure function of them, which velocity structure function, very briefly, it's look at the correlation between the velocity difference between each of the stars versus their separation. And if there is turbulence, it would we would expect a power law correlation between the velocity difference and the separation. And so we did that, and in addition to the 5 groups, we also separated Orion A, which includes the Orion Nebula cluster, which is the thing you're seeing behind me right now. And we separate this Orion Nebula cluster from Orion A because it is a very dense cluster of stars, which raised some interesting theoretical aspect to it. Because in addition to what we expected, which was turbulence that comes from the formation of stars out of turbulent interstellar medium gas. These stars that are very close together frequently dynamically interact with each other. So they also experience rapid dynamical relaxation in addition to the turbulent. So their memory got partially erased, which you will see later in the paper in one of the figures that we have. So we found that both the all of the diffuse group has power law correlation that that exhibit very strong evidence of turbulence, while the Orion Nebula cluster has an almost flat spectrum, which indicates that there is almost no turbulence, or that the turbulence has been erased.
Cool.
And there was one more thing that we were able to detect, or at least partially verify, which also came from another paper from Marina in 2020, which was when she argued that there was a supernova explosion that went off in the heart of Orion around 6 million years ago that created the Barnard's loop. And in the feature of the velocity structure function spectra, we saw a sign of a local energy injection that could be contributed by the supernova.
Okay.
Okay, so I think we can go to the first figure.
Let's take a look. Here's the.
It's slightly.
Yep. Just no.
Yep.
All right, here we go.
Right. So in the first figure, this is just a an overlay plot of the Orion complex. So it is in the background, that's a black and white photo of the Orion complex in both the infrared and the visible spectra. And you can see on the top left is Betelgeuse, and the bottom right is Rigel. And also there are the 3 stars in the Orion belt that is kind of hidden behind the field of stars in the cyan and red right there. And so each of these color correspond to a group that we analyzed. And as you can see, the yellow and the green, so originally in Marina's data, they are in the same group, which is called Orion A. However, we separated them so that you can see that the Orion A, for us, is kind of the tail of the Orion Nebula cluster, which is really dense, and you can see how dense it is by the color and the frequency of dots within that small area. While other groups like Orion D and C are fairly diffuse, and then Orion B, which is this light purple color, it is consists of 2 smaller cluster. So one on kind of the left side and one closer to Orion C. And then there's another group that is isolated to the north of Orion A to D, which is the Lambda Ori. And there's also a smaller, very dense cluster in the middle of Lambda Ori, which you can see kind of like the black dots in the middle of all the purple stars right there. Right, so each of these dots is one of the stars that we analyzed in our paper. And in total, there were 1,439 stars.
Nice.
Before we move on, I would just like to point out that the bubble-like thing, the pretty big structure that we see here in black and white, is the Barnard's loop.
Yep.
And we think that was created by the supernova explosion.
Mm-hmm.
Okay.
I believe that.
So other than that, I think we can go to figures 2.
Okay.
Right. Which is very briefly, we just wanted to show the this figure was plotted to show the seemingly random distributions of stars velocity in each of the groups. So plotted is the velocity space of so we converted all of the stars from the RA and DEC and with parallax into the X, Y, Z coordinate. So just Cartesian coordinate, and then we plotted the velocity of the stars in all 3 dimensions. So Vx and Vz in as points on the plot, and then Vy as a color plot. And Vy is very closely related to the line of sight velocity of each of the stars. So as you can see, like they are pretty random. Like there's no clear structure to how the star's velocity are distributed. There's no clear rotation or like one the direction of motion for all the stars. It's kind of all over the places. So we want to show this because this is what we would have seen if we just look at the raw data.
Right.
But hidden behind this randomness is it's actually structure that comes with it. And we can see that structure in figure 3.
Revealed. All right, here we go. Right there.
Right. So, okay. So figure 3. So all the figure 3 plots are the first order velocity structure function of stars in each of the groups. And then the last 2 panels are the combined structure function with and without the Orion Nebula cluster. And as I mentioned before, the y-axis is the absolute value of the velocity difference between the stars. This is the difference in velocity vector because we have 3D velocities versus the L, which is the separation between stars, and then we average those into around 40 bins. Starting from 1 parsec to about 170 parsecs.
Okay.
Yeah. So we plotted.
So let me just make sure I'm clear. So the y-axis, I get that, it's delta V, and that's what you're calling a velocity structure function.
Right.
Okay. And then so you pick a star.
Mm-hmm.
And now to make these plots, you go to every other star in its neighborhood, right?
Right.
I'm with you. Go ahead.
Okay.
All of the stars, not just in the neighborhood. So for every group, you're looking at the possible combinations of pairs.
Yeah, within the group.
Yeah.
Exactly.
Yeah. And then the last 2 are looking at all of the stars together.
Right. Okay.
The last 2 panels.
I'm good. I'm with you.
Okay. Yes. So as you get, and then we also plotted, in addition to the velocity structure function, we also did kind of like a Monte Carlo, well, it's a random sampling method by generating 1,000, a sample of 1,000 stars with properties within the error of measurement given by Gaia to estimate the error of the measurements. And those are shown by these arrow bars, vertical arrow bars. And also, we plot 3 lines to guide the eye, which the solid blue line is the Larson's relation for velocity dispersion relation for gas in molecular clouds in the Milky Way, which is a 0.38 exponent, like power correlation. And then the black dot dash line is a 1/3 power law, which is the Kolmogorov, or the for incompressible turbulence.
Yes.
And then the pink dash line is the 1/2 power, which represent the power law for compressible turbulence or supersonic turbulence.
Yes.
Okay, so what we see in general is that all of these groups they exhibit a clear power law correlation. Some of them are well, most of them are close to a Kolmogorov, but some of the interesting ones are as you look at Orion D, it is both higher than the line of the Larson's relation, and it is steeper. So its magnitude is higher, and its slope is steeper than Orion, than the Larson's relation, sorry, accumulated to a bump at around between 60 and 70 parsecs. And so this shows that, first of all, there is a supersonic turbulence driven, supersonic driven turbulence in the velocity structure function of Orion D, and that this bump, when we compare with the age of the stars in Orion D, and the I'm sorry, I kind of have to slow down a little bit and kind of think about what I'm saying. So this bump, when you compare it with the age and the velocity that this bump is at, which is around like 7 kilometers per second at the highest peak, this corresponds to the size of Bernard's loop, which is, if I remember correctly, it is about 80 parsecs in diameter. And in Marina's paper, she argued that there was a supernova around 6 million years ago. So this very closely corresponds to shows that the supersonic turbulence was driven by the local energy injection from that supernova. And
yeah, I should
Dr.
just
Lee, if you want to
add a little bit. So a lot of the stars in Orion D actually were created after the supernova went off.
Okay.
Actually, Orion C as well. So you probably don't remember the first figure, but basically C and D are closer to, yeah, okay, maybe if we can, sorry, yes, thank you. So C and D, yeah, red and cyan are closer to the explosion center, whereas A and B are a little bit further away. It's a little bit hard to see because it's projected, but just trust me. A and B are a little bit further. C and D, so C and D are expected to have been influenced by the explosion more than A and B. And we see this in the structure function, as Trung explained, both in terms of the amplitude, so just the level of turbulence for C and D, right, are they above Larson's law. So the amplitude is higher, meaning there's just more kinetic energy in turbulence. And then if you look at D, it's also steeper, possibly because it's more related to the shock wave. So it's more supersonic. And interestingly, you can even see where the energy is being injected, like what scale it corresponds to from the structure function, exactly. And we can estimate when the stars in Orion B, most of the stars in Orion B formed, how big that Barnard's loop would have been based on how big it is now and how fast we think it's expanding. And that's more or less how big it would have been when most of the stars in Orion D formed. Cool. So everything seems to be, in agreement. And it's, so then if you look at A and B, in terms of the amplitude, they're more or less at the Larson's law.
Yes.
Yeah.
Yes, got it. I'm with you.
Okay.
And then ONC, what's up with ONC?
Right. Right. So for ONC, as you can see, it's basically almost flat. And this flatness is, we can attribute it to, how densely packed the stars form in the nebula cluster is. So when they are so densely packed together, right? In figure 1, we can see that when they're so densely packed together, they constantly undergo
scattering.
Scattering and the dynamical interaction with each other. And these dynamical interaction basically erase all the memories of their original motion that they inherit from the natal clouds. And because of that, the memory of turbulence is erased. And then we can see that reflected in the slope of the velocity structure function of ONC, which is basically flat. Yeah. And if we look at the very last panel, which is the combined plot of all of the stars in Orion complex, or with ONC, we can see 2 dominant structure. So from 1 parsec to around 20 parsecs, the spectrum is pretty flat. So this is because all the stars, or at least most of the stars in the Orion Nebula cluster, are densely packed together. So their distance, most of them are between 1 and 20 parsecs away from each other. And in addition to that, there were 585 stars in the Orion Nebula cluster within our sample. So that's why if from 1 to 20 parsecs, the velocity structure function spectrum is dominated by the feature of ONC. And then from around 20 to 70 parsecs, the second most populated populated groups in our analysis is Orion D with around 343 stars. And so it reflects in the spectrum from 20 to 70 parsecs that the slope follows that of Larson's law. So the slope is pretty close to around 0.38 or 0.4. And that makes sense because it's dominant. It's the second most populated group, and also their relative distance is mostly in that range.
And I would also add that in ONC, so this is something I didn't know before. I sort of knew about the 2-body relaxation. So in the star cluster, a star would have gravitational attraction with nearby stars. But what one of the other co-authors, Hui Li, who was actually a a theoretical expert on star clusters and star formation. He educated us on what might happen to a very dense cluster like O and C, which is basically you can have interaction between individual stars and the whole gravitational potential of that whole thing. Yes. And so when the star cluster is forming, it's relaxing, dynamically relaxing as it's forming. Of course, we can also just calculate the two-body relaxation time, and that's already pretty short for a dense cluster like this. So we estimated that the relaxation time is much shorter than, well, not much, but it's shorter. The core relaxation time of OpenC is shorter than the age of the system.
Yeah.
Yep. Yeah. So it has pretty much relaxed in the center. Yeah.
Right. Cool. Very cool.
Yeah.
Very
and
nice.
You can see a little bit of the influence of these tiny little star clusters in the other groups, as Charles mentioned. I think Orion B has 1 or 2 star clusters in the center, and then maybe Lambda Ori. So a lot of these loose groups might also have 1 or 2, little dense clusters within. And we think that that might be the reason why we see a flattening of the velocity structure function on small scales almost in all of these loose groups, right? Of course, the error bars also get larger just because you have fewer pairs of stars with such small distance. But I do think the flattening is real, and it's partially due to these teeny little star clusters that have relaxed or partially dynamically relaxed and forgotten about this power law scaling relation that they should have.
Yes.
Yeah, and then there are other possible contaminations from other sources. For example, binaries. Marina had removed all of the binaries with really, really large velocities. So when she was grouping things together, if anything had weird velocities, then it would have been thrown out.
Okay.
But I think we would still have allowed binaries with velocities below like 3-ish kilometers per second.
Right. So a wide.
So, yeah. And if we only look at one of the stars, well, so with binaries, we should be looking at the center of the mass and how that is moving. Of course, that's not what we see observationally. We'll be looking at individual stars, and there's no way for us to tell which is which. And so we would just include all of the motions as the motions of this turbulence, even though part of that could just be from the binary motion. And so there would be, I like to think that there's almost like a noise level at about 3 kilometers per second, which is also more or less where the velocity structure function flattens. Yeah, so I wouldn't trust anything below that velocity. So 3-ish kilometers per second and below would be partially contaminated by binaries, possibly contaminated by these tiny little star clusters, and a few other things. But for scales above, let's say a few parsec, definitely above 10 parsec, I think our measurement is pretty reliable.
Cool.
Yeah.
Very cool. I think we got one more.
Oh, one more in the appendix. Nah, not important. It's okay. We can briefly mention it. So we also looked at higher order structure functions. So that's the last plot. Yeah, in the appendix. Yeah.
Yes, we did. Okay.
Yeah. Because sometimes if you just look at the first order structure function, you can't be sure that you're looking at turbulence. This is just to help us feel more confident that it is indeed turbulence, because we can look at higher order structure functions and they all behave as one would expect.
Cool.
Yeah.
Very good. Awesome. Very good. Better be careful there. You're going to have to give up black holes and become a observational turbulence person. So let me ask, where do we go from here, given that this is a letter and this is the first shot at it? So are there Are there new observations that would take us to, let's say with DR3, would there be 10,000 stars? Are there additional observations planned?
Yes.
Where do we go over the next 5 years?
Yeah. Trung, do you want to start?
Sure. Okay. So I think one of the biggest challenges we have is that we want ideally 6-dimensional data. And for a majority of data coming from Gaia, they do not have the line of sight velocity or radial velocity. So there's only a very small sample of the stars. I think out of the 1.3 billions that they mapped, they only had about 10 million that has radial velocity measurement. So when as that number expand and we have more stars recorded with radial velocity, we would like to look at more groups around in the Milky Way, ideally in like closer star formation groups and structure in the Milky Way to continue this work and verify that we also see the same turbulence in other star forming regions.
Mm-hmm.
Cool. So Frank, you can see how spoiled we are. Trung is talking about not having 6-dimensional information.
My heart is bleeding for you.
But actually,
a full state vector. What's wrong? Well, I would think then that on some of these things, people could do follow-up radial velocity surveys for some of this stuff.
Yeah.
Yeah.
And we do have 6-dimensional information on a few other clouds, and Trung is looking at Taurus, which is exciting because in Orion, I was hoping, before I started on this, I was hoping we could compare turbulence measured by stars and turbulence measured by gas. And you know what? That supernova explosion destroyed most of the gas in Orion.
Yeah, you've got a lot of things going on there. So
yeah, there's not much left. There's a little teeny little bit, but like I said earlier, we don't really fully trust our measurement at very small scales. And then the gas measurement is all about small scales because most of the gas is gone. Right. So we can't do that for Orion. So hopefully we can do it for Taurus because Taurus is not destroyed. Yeah. And we can definitely, and we will look at this in Huili's simulation. So Huili, like I said, he's a Hubble fellow at Columbia right now, and he's done these amazing high-resolution molecular cloud star formation simulations. So we can go into the simulation where you can always get 6-dimensional data, right? 7-dimensional because you also have time. Yeah. And then look at how turbulence traced by stars would evolve with time because there's relaxation. There's also just stars drifting away from their original position in the phase space, right? Or velocity position space. So we don't really know we don't really know what to expect. We sort of have some ideas from the back of the envelope calculations, but it'd be nice to actually measure these things in a simulation so we know what we're actually looking at when we look at the real data. And also, I don't know what to expect in terms of the turbulence traced by stars versus turbulence traced by gas. Now we would naively assume that turbulence traced by stars would be exactly the same as turbulence traced by the very dense gas. And I think we like Chung's got some preliminary results on Taurus that seems to show that. But then what about the slightly warmer gas, right? Would that also follow the same kind of turbulence or it's higher level, lower level? Yeah, it's all things that we can explore and think more about. Yeah, and also there are things one can do with 5-dimensional data as well. Now, before our work, right, all of the turbulence in the interstellar medium or anywhere else was measured with gas. And we never have 6-dimensional information on gas. We only have line of sight velocity. We never know how gas is moving across the sky. We don't ever know its exact location. We know its position and projection, but not the correct precise distance, right?
XYZ.
Yeah, so I think even with 5D data, we can do a lot of things as well.
Cool.
Yeah.
Sounds like there is a lot of juicy science to be taken out of this orange over the next. I think I know what somebody's thesis is going to be.
Half.
No, there'll be a lot of work in this, I think, over the coming 5 years or so. So it's very cool. It's very cool. Nice first shot. And so Trung and Yuan, I want to thank you so much for spending some time and walking us through your really lovely letter today.
Thank you.
All righty. Thank you, everyone. And we'll see you on the next one. Bye-bye.
Bye.